Anna Markov works as a quality inspector for a company called Normal Distributors. The company has manufacturing plants in 5 cities. Anna routinely conducts surprise inspections at each site to check for abnormalities. She flies from city to city randomly through airports with direct connecting flights. Every time she performs an inspection, she stamps her logbook. Then she selects the next city she will fly to randomly from all available connecting flights with equal probabilities. The 5 cities are Averagemont, Bayesville, Continuopolis, Discrete-Town, and East Vandermond. Not all of these cities are connected via direct flights to each other. For example, there is a direct flight from Averagemont to Bayesville, but not from Averagemont to East Vandermond. In the long run, which city do you think she will spend the most time in? A. Averagemont, B. Bayesville, C. Continuopolis, D. Discrete-Town, E. East Vandermond, F. About equal among the 5 cities, or G. It depends on which city she starts out in. Today, Anna is in Bayesville. She uses a spinner to pick randomly from all available cities with equal probabilities. Bayesville is a major hub and has direct connections to all the other cities. The spinner lands on Averagemont, so that is her next stop.
Just another average day in Averagemont.
After she finishes her inspection, it's time to choose the 3rd stop. Let's see where she lands next.
Bayesville again? Why do I keep ending up in Bayesville?
Now it's time for her to pick the next stop.
Oh, great! East Vandermond. I haven't been there in ages.
East Vandermond is more remote and only has flights back to Bayesville, so she will definitely go back to Bayesville next.
Why am I even bothering with this silly spinner? If I keep doing this, I wonder, what fraction of my time will I end up spending in Bayesville?
The process that Anna is following is an important example of a Markov chain. The Markov property means that at each time point, determining the next city that Anna will go to depends only on where she currently is and the randomness of her spinner. Given the present, the future is independent of the past. This is a form of memorylessness. Given her current location, her past history is irrelevant for predicting where she will go next. To answer Anna's question, let's consider the following problem. In the long run, as Anna continues this random process, what percentage of her time will she spend in each city? Let's plot this after various numbers of trips. We have 1 bar for each city, and the height of each bar indicates the percentage of time Anna has spent in that city overall. In our simulation, here is how the distribution looks. At first, the plot was fluctuating a lot, but now it seems to have stabilized. The distribution it has stabilized to is called the stationary distribution of the Markov chain. We are showing one particular run of the simulation, but Anna's process will always converge to the same stationary distribution no matter which city she starts out in. It turns out that the percentage of time Anna spends in a city is proportional to its number of connections. For example, Bayesville has 4 connections and East Vandermont only has 1. So Anna visits Bayesville 4 times as often as East Vandermond in the long run. The network structure is the key to determining the stationary distribution.